Hello. My name is Japheth Hayman. I'm an undergrad researcher here at the University of Alabama in Huntsville. My advisor is Dr. Judy Schneider in the Mechanical and Aerospace Engineering Department. This is Additive Manufacturing in Space, a companion presentation for the Honors Capstone research poster by the same title. So the driving issue here is the desire to explore further into space. And as we do that, we need to build outposts where we can stop and make repairs. Just like when humans were first exploring the oceans, nobody went too far from home without first establishing ports where they could stop and fix their ships as well as restock on supplies. So we need places out in space, apart from the Earth, where we can manufacture replacement parts, new tools, and just generally recycle and reuse the things that we already have. The issue there is that most of the manufacturing methods we use here on Earth require a factory or a foundry or some other bulky installation. Now, when you want to build a factory on Earth, you can buy your materials, have them brought in on a truck, and if your order is big enough, you get free shipping. That's not how it works in space. Every ounce of material costs fuel and it costs space on a craft. So it's way too expensive to try to build a factory on the moon, let alone on Mars or on one of Jupiter's moons. For the same reason, we don't want to be hauling up raw materials for the manufacturing. So we need a system where we can manufacture things without a bunch of infrastructure and without needing to bring up raw materials from Earth. And we think additive manufacturing is a way to do that. However, in additive manufacturing, there's some uncertainty as to what type of feedstock is actually optimal. What we do currently is there's stuff made for other processes. There's powders made for powder metallurgy and wires made for fusion welding. And from those options, we say, oh, this works for additive. But we don't really have any feedstock that's specifically developed for additive manufacturing, so we don't know exactly what is optimal. In this study, we're looking at two types of additive manufacturing, both of which are powder-based. The first one is laser powder bed fusion, or LPBF. In this process, you deposit a whole layer of powder in the powder bed. Then you come back with a laser and you melt the shape of your part. Then you let that whole layer cool, and then you deposit a new layer. So it's cyclical in this way. And on Earth, we normally rely on gravity to hold the powder in place as we're doing this, but there's some proof of concept work going on that shows that this can actually work in microgravity, which means that powder bed fusion is viable in space. The other method we're looking at is laser blown powder deposition. Whereas powder bed fusion rotates through the different stages, blown powder does it all at once. So you have this gas that's depositing the powder, and at the same time you're melting it with a laser, and as you're moving along, the material behind it is cooling and solidifying. So between the fact that the powder is moved by gas rather than gravity, and it's melting and more importantly sticking as it's hitting the substrate, we think that this method will also be viable in space because it seems that it relies very little on gravity. While of course we don't know in practice, in theory this will work. So these two different methods have different requirements because they're relying on different mechanisms. So what we think is that flake-shaped powders will be better for powder bed fusion because they're going to pack better and stay in place in that powder bed, whereas spheroidal powders are going to be better for blown powder because they flow better. Now, meteorites, along with meteoroids floating out in space, and even asteroids, which are just bigger meteoroids, they're full of iron, actually iron and nickel, but here we're focused on iron. We can put that through electrochemical processing, a method called selective electroplating, and we can extract pure iron from these meteorites that we can collect off the surface of the moon or Mars or wherever else. Anywhere that a meteorite has impacted, there are likely to be fragments that we can process and get the iron out of. And the reason we're focused on iron is because it's the most common structural metal that we use today. Now, when we do this electrochemical processing, we get these irregular flakes. And so the big questions here are, can we use these flakes directly for powder bed fusion, which we hypothesize works better with a flake-shaped powder? And is there anything we can do to spheroidize these flakes to optimize them for blown powder processing? In an attempt to do this, we used ball milling. Now, high energy ball milling absolutely does spheroidize particles. It partially melts them so that they reform and they're round when they come out. However, we did not have a high energy ball mill. What we had was a speed mixer on loan from Flak Tech with ball milling inserts, so not quite as fancy, not quite as high tech. And at the energy levels we had, we were able to refine the flakes, but they didn't melt at all, so they didn't spheroidize. Now, here we have a summary of the actual results of the processing. The main takeaways here are that after ball milling, the flakes were smaller, but they were definitely still flakes, and they were actually more irregularly shaped. The aspect ratio went up, the circularity went down. And what that points to is the fact that, again, the flakes weren't reshaped, they were only broken apart. So we have these larger pieces that were maybe halves of the original flakes, and then a bunch of these little tiny pieces that probably broke off in between. Now at the bottom of this table here, we have the Hall flow rate, which is in seconds per 50 grams. That's time per unit mass, which is the inverse of what we would usually think of as a rate. And so when we see that this reference material, the Inconel 625, which does get used in blown powder processing, we see that has a Hall flow rate of 12.2 seconds per 50 grams. When we look over to the ball milled flakes, we see that it's about 2.5 times higher Hall flow rate, which actually means that it's 2.5 times slower. In the same way, the as extracted flakes are about 3 times slower to flow than the reference Inconel. And all that again is because spheroidal powders will flow more readily than flakes. So we took our two flake-shaped powders and tested them in the additive processes that we were looking at. So we used the raw as extracted flakes, the bigger ones, in powder bed fusion, and then we took the ball milled flakes and tested those in blown powder deposition. Now we have at this point done some testing on both of those builds, but that is beyond the scope of the summer research. To hear about that testing that we've done, be on the lookout for the write-up, which will be in Perpetua, our UAH undergraduate research journal, hopefully this fall semester. If not, then definitely in spring of 21. You can also contact me at the email address on screen to ask any questions, as well as keep up with any future publications, including conference presentations. As I'm recording this, I actually just finished a presentation, so be on the lookout for all of that, and thank you.